Good day, everyone. I am Alona Mae M. Camacho, and I will be presenting my thesis entitled Photocatalytic Degradation of Polycyclic Aromatic Hydrocarbon (PAH) Anthracene using Cobalt-Doped Zinc Oxide. To introduce you to my study, I will start with anthracene. It is a hazardous PAH that poses significant environmental and health risks due to its toxic, combustible, and carcinogenic properties. Found naturally in crude oil, coal, and gasoline, anthracene is a major contributor to pollution, affecting air, water, and soil. Its environmental persistence and bioaccumulation in living organisms make it a serious threat, leading to long-term detrimental effects on ecosystems and human health. Photocatalysis is a process that utilizes light and a semiconductor to alter the rate of chemical reaction upon exposure to sunlight. To introduce photocatalysis as a practice, I have cited some references. Photochemical oxidation, employing semiconductors like titanium dioxide, zinc oxide, tungsten oxide, and aluminum oxide, has proven to be an effective technology for the mineralization or partial oxidation of various organic pollutants. Although zinc oxide has been widely investigated for photocatalysis in water to degrade organic compounds, limited research has focused on its utilization for the photocatalytic degradation of anthracene specifically. Recent experiments have demonstrated that zinc oxide, along with materials exhibiting longer transient times, can significantly enhance the photocatalytic degradation of anthracene. These materials also show higher quantum efficiency as they absorb more light in the UV region compared to other photocatalysts like titanium dioxide. Despite the relatively fewer research materials available for zinc oxide compared to titanium dioxide, they possess similar advantages. The following are the objectives of this study. First is to evaluate the degradation efficiency of cobalt-doped zinc oxide nanoparticles in the degradation of anthracene by measuring the reduction in concentration over time using UV-visible spectroscopy. Second is to support the results of this study with kinetic studies such as the Lamimer-Hinshelwood theorem. Third is to synthesize cobalt-doped zinc oxide nanoparticles and characterize their structural and functional properties using X-ray diffraction, Fourier transform infrared spectroscopy, and UV-visible spectroscopy. The significance of the study lies in its environmental impact, wherein, as mentioned before, anthracene is considered a persistent organic pollutant due to its nature. And in scientific advancement, exploring cobalt-doped zinc oxide as a novel photocatalyst can lead to enhanced designs of photocatalytic systems by enhancing photocatalysts such as zinc oxide. And in the research gap, there is a lack of research on the photocatalytic degradation of anthracene using modified zinc oxide. For the review of literature, I want to first establish the practice of photocatalysis. It is not a brand new concept. It has progressed reasonably well because of other studies used as a foundation for its different applications. For example, research on nanomaterials over the decades has built a knowledge of their charge behaviors, resulting in improved applications of quantum confinement in photocatalysts. The past few decades have observed an increase in using semiconducting oxide photocatalysts due to their potential to treat organic contaminants found in soil, water, and air. This method was developed around the 1970s and has since been applied in decomposing and mineralizing recalcitrant organic compounds. Photocatalytic reactions touch the optical and electronic properties of the material. Therefore, photocatalysts such as studies on 2D photocatalysts contribute to advancement in materials characterization. These advancements made forming nanomaterials and photonic structures possible. Tools for the characterization of new materials are essential for future development and serve as a solid foundation for techniques in photocatalysis. This information makes research on photocatalysis necessary as it encompasses research on materials to be used, which includes understanding that this is a whole topic essential to classify materials according to their function. This advancement is also an advancement that one can apply to future research and applications. Humankind is exposed to many pollutants, and one of the most concerning and highly toxic pollutants is petroleum hydrocarbon byproducts. It exists in our energy use on a large-scale basis and is present in household products such as cooking oils, which explicitly hold PAHs. The risks include damaging organs or even systems of the body, nervous, immune, and reproductive systems, to name a few. Anthracene is a solid PAH composed of three fused benzene rings in crude oil. It mainly acts as an allergen and irritant to the eyes, nose, throat, and skin. It is also classified as carcinogenic, which may lead to mutations. They are incredibly persistent in the industrial wastewater. Humans are primarily exposed to this pollutant through tobacco smoke and ingestion of food contaminated with combustion products. For this study, the organic pollutant anthracene will be degraded. Geographically, the Philippine Sea, situated at the Western Pacific Ocean, is susceptible to various atmospheric and hydrologic dynamics. This creates a situation where a lot of PAH are distributed in many other areas, especially during monsoon periods. Moreover, Philippines is in the Pacific Ring of Fire where most volcanic eruptions occur, which is a big contributor to the production of PAHs. Heterogeneous photocatalysis comes up in many forms through semiconducting oxide photocatalysts. In this regard, titanium dioxide is the most commonly used photocatalyst in the photodegradation of organic pollutants. It is highly regarded for its photostability, low cost, chemically and biologically inert nature, and absorbing capability. In a study by Gaya and Abdullah, titanium dioxide was analyzed and compared with other photocatalysts. The closest to the efficiency of titanium dioxide in its anatase form is that of zinc oxide. Zinc oxide is observed to be of higher efficiency when its structure is crystalline and of smaller crystallized size and particle size. There are reports suggesting that the optimum size is in the range 7 to 15 nanometers for various photocatalytic reactions. In another study, zinc oxide nanohybrid shows promise when designed to be sunlight active. It achieved the complete removal of pollutants from a water sample. This result provides insight and potential into zinc oxide as a viable photocatalyst comparable to titanium dioxide. This study is challenging to find the best alternative and contribute to the decades of research that studies photocatalytic degradation. The methodology will have the following flow. For sample sourcing, all chemicals used in this study will be sourced out locally and of analytical grade. The chemicals used are listed below. To create cobalt-doped zinc oxide nanoparticles, the chemical co-precipitation method will be used. For the synthesis, zinc oxide was dissolved in 1 acetic acid and cobalt chloride was dissolved in deionized water at room temperature. There are three variations of dopant concentration, 5%, 10%, and 15% by mole, and it all underwent the same process only with different mole concentrations. The precursor solutions were mixed for 30 minutes to ensure complete mixing and then continuously stirred, while 0.1 m sodium hydroxide was added dropwise to achieve pH level 10. The precipitates formed were filtered in a Buchner filtration setup and was then washed with deionized water and ethanol to remove residual reagents and impurities. The filtered precipitates were then dried in an oven for 1 hour at 120 degrees Celsius and then annealed for 3 hours at 300 degrees Celsius. The synthesized photocatalysts were then characterized by FTIR, UV-Vis, and XRT. For the preparation of synthetic wastewater, anthracene was received without further purification. A stock solution of 40 ppm composed of dissolved anthracene and ethanol was prepared to get a homogeneous solution. The stock solution was diluted to create anthracene solutions with concentrations of 20, 30, and 40 ppm to create the working solutions that will be used in the photocatalytic degradation tests. To measure the concentration of anthracene in the solution, UV visible spectrophotometer was used. In the utilization of UV spectrophotometry in characterizing, co-ZNO was mixed with ethanol and run at a range of 200 to 600 nanometer. The black solution used was ethanol. The bandgap energy was calculated using the talc method, and the formula used is the following equation from Akhtar et al. 2020. To evaluate the photocatalytic degradation of anthracene, UV-Vis was also used. A concentration of 0.02 gram per liter of the photocatalyst was added to the varying concentrations of anthracene. The solution was stirred in the dark for 30 minutes before being exposed to visible light to establish adsorption-desorption equilibrium between the photocatalyst and the anthracene solution. Alicos of 5 ml were taken at the regular intervals of 15 minutes to measure the concentration of anthracene in the UV-Vis spectrophotometer at a range of 200 to 600 nanometer. The experiment ran for 4 hours for each test. The alicose obtained was centrifuged and isolated to supernatant, which was then assessed in the UV-Vis. The results obtained from this method was then compared to the photocatalytic performance of pure zinc oxide in the same experimental conditions as co-ZNOs. A pseudo-first-order kinetic model is applied to describe the rate of the chemical reactions that occurred in the course of the experiment. The Langmuir-Hinshelwood kinetics equation that was used is as follows. The structural property of the synthesized co-ZNO nanoparticles was analyzed under FTIR. The characterization of ZNO and co-ZNO samples reveals a significant influence of cobalt concentration on the measured property. In the pure zinc oxide sample, there is a strong absorption band below 600 per centimeter, indicating the presence of ZNO and exhibiting a stable baseline. Upon cobalt doping, the peak undergoes a noticeable shift and broadening. For the 5% co-ZNO sample, the ZNO stretching vibration shifts slightly, suggesting effective incorporation of cobalt ions into the ZNO lattice, which modifies the local bonding environment. Increasing cobalt concentrations to 10% and 15% result in further peak broadening and intensity reduction, signaling increased lattice distortion and defect formation. These changes imply that although moderate cobalt doping can enhance structural and electronic properties favorable for photocatalysis, excessive doping introduces disorder that may adversely affect material performance. In addition, the 5% co-ZNO sample had the highest stable value compared to the other samples, suggesting enhanced properties or stronger response at low doping concentration. The 10% co-ZNO shows a moderate increase in transmittance but remains below the 5% co-ZNO sample. Its curve is smoother and the rest of the line has more stability, indicating a more uniform behavior than other samples. The 15% co-ZNO sample has the lowest transmittance values than the rest, indicating a decline in the structural property with higher cobalt doping. These are the top plots generated from the UV-Vis characterization and the formula mentioned in the methodology. These results in the table are consistent with the typical direct bandgap of zinc oxide reported in the literature, which generally ranges between 3.2 and 3.4 electron volts. A slight reduction in bandgap energy to 3.23 at 5% doping suggests a redshift, indicating that the material can absorb photons of lower energy, extending the absorption edge closer to the visible light region. It's beneficial for photocatalysts because it allows the catalyst to harness a larger portion of the solar spectrum, especially visible light, which constitutes the majority of sunlight. At higher cobalt doping concentrations, the blue shift or slight bandgap widening observed suggests a partial restoration of the intrinsic ZNO band structure. The shift may reduce visible light absorption slightly but could also enhance charge carrier separation by reducing recombination centers associated with defects present at lower doping. The improved crystallinity or reduced effect density at higher doping levels can lead to longer-lived charge carriers, which is critical for efficient photocatalysis. However, excessive doping can lead to clustering or secondary phase formation, which might adversely affect photocatalytic activity by acting as recombination centers or blocking active sites. Cobalt-doped zinc oxide samples reveal a hexagonal word-site ZNO structure with the three strongest reflections observed listed in this slide. These peak positions align well with standard zinc oxide patterns, indicating that cobalt ions are successfully incorporated into the zinc oxide lattice without the formation of secondary cobalt oxide or metallic cobalt phases. Table 3 summarizes the analyzed XRD results to express the lattice distortion and crystallite size of the cozinos, where the values are calculated in accordance with the characterization study by Shunmuga et al. Under the synthesis condition and doping range, cobalt seems to promote grain growth due to the increasing crystallite size with higher doping, suggesting that cobalt incorporation leads to a modest lattice expansion. This is likely due to a local strain relaxation or possible dopant clustering with higher doping. The trend of increasing crystallite size, along with decreasing strain as cobalt increases, is consistent with dopant-induced grain growth and reduced strain. Moreover, the observed reduction in lattice strain with higher doping levels supports the idea that increased cobalt concentration promotes improved crystallinity and structural stability, implying that the dopants entered the bulk lattice. There are very subtle changes in the lattice parameters due to substitutional incorporation of cobalt ions, as the cobalt ions replace zinc ions in the crystal structure. The ratio of the lattice parameters has a standard value of 1.6. This is consistent with the values obtained in this experiment, indicating a good correlation and suggesting that doping of cobalt took place without affecting the overall structure. The highest percent degradation out of all the photocatalysts came from the 5% co-ZNO samples, averaging at around 50%. The lowest degradation efficiency came from 15% co-ZNO samples on all concentrations of anthracene. Figure 8 also dictates that for co-ZNOs, the higher pollutant concentration results to higher degradation efficiency, and that for pure zinc oxide, the lowest pollutant concentration yielded better result in comparison to other pollutant concentrations. It is observed that the pure zinc oxide and 10% co-ZNO exhibit similar max degradation efficiency, which makes sense in the characterization mentioned earlier because they had the most similar values in the analysis. Supporting the use of this analysis, the Langmuir-Hinshelwood model of the experiment is shown in this figure. A plot of LNCT over C0 by irradiation time at T1 to T16 where data points have a 15-minute interval each. In this figure, the general trend is that 5% doping indicates enhanced degradation rates compared to pure zinc oxide and other cobalt doping concentrations. This suggests that although cobalt doping can improve photocatalytic activity, there is a threshold wherein cobalt doping may be too much and it could decrease the photocatalytic activity under visible light. This is evident especially on the 15% co-ZNOs, where the trend indicates that absorbent values of anthracene were not decreasing but increasing. In a study by Salute et al., anthracene was determined to have degraded and produced byproducts such as anthrone, 9,10-dihydroxyanthracene, and 9,10-anthraquinone, which was observed when the degradation efficiency of their photocatalysts would decrease after increasing initially. This behavior of anthracene mirrors the results of this study, indicating that the anthracene did not just degrade but also created byproducts or intermediates. This does not necessarily mean that remediation of anthracene was unsuccessful due to the identity of the byproducts. Anthracene is a persistent organic pollutant, and the byproducts mentioned were all less persistent and more susceptible to degradation due to their higher activity and biodegradability, reducing long-term environmental impacts. The experiment also observed that all photocatalysts, except the 15% co-ZNO, would degrade properly in the beginning of the runs, but would later produce intermediates or byproducts. Zinc oxide produces the least number of byproducts, judging by the behavior of the lines in this figure. It plateaus in contrast to the 5% and 10% co-ZNOs, where they observably create a positive slope at different time points. It may have also formed byproducts that are stable and resistant to further degradation. The 5% co-ZNOs would start their positive slope after T time point 11 or time point 12, where these data points are at the 165 and 180-minute marks of the experiment. The 10% co-ZNOs, on the other hand, would start their positive slope after time point 6 or time point 7, which means they reach their maximum degradation between 90 to 105 minutes. The positive trend in the kinetics after those specific time data points may be explained by the formation of byproducts or occurrence of secondary reactions, both of which are out of this experiment's scope of analysis. To conclude, the structural and optical analysis indicates successful doping through substitutional incorporation of cobalt into zinc sites, which is bulk doping. The 5% and 10% mostly show substitutional doping, but the 15% co-ZNO shows some clustering. The photocatalytic degradation tests of anthracenes revealed that 5% co-ZNO has the highest degradation efficiency across all anthracene concentrations. The formation of intermediates and byproducts during degradation reduces photocatalytic efficiency. The 5% co-ZNO significantly outperforms pure zinc oxide. 10% co-zinc oxide shows only a slight improvement over pure zinc oxide. 15% co-ZNO fails to degrade anthracene effectively and rapidly forms intermediates. Low-level cobalt doping improves the zinc oxide photocatalytic performance, but excessive doping leads to byproduct formation and decreased efficiency. For recommendations for further studies, in a study by Dina et al., they showed that co-ZNO photocatalysts have high stability with minimal performance loss after recycling. This recyclability could improve the sustainability of pollutant remediation methods used here. Also, adding additives during synthesis could help control the morphology of cobalt-doped zinc oxide, especially with higher concentration of cobalt doping. Research should also explore the effects of parameters like pH levels and catalyst dosage. Optimizing catalyst dosage is important as it influences byproduct formation, an undesired factor in this study. Also, identifying compounds in the supernatant could clarify byproduct formation and guide improvements. This can be done, for example, by the use of GCMS. That's all. Thank you.